This is a video about Kirchhoff's rules, in case you were wondering about the double H. Where Kirch comes from, Kirche, church, Hoff is yard. So this is like the entire church grounds. It would include the graveyard, but also just the entire church yard, German. That aside, we have two rules. One, the current going into a junction is equal to the current coming out of a junction. And that one should be fairly logical. The current has to go somewhere. It can't just disappear and we can't make new current. And two, all the potential in any closed loop has to be accounted for. So what this looks like in practice is this. If I've got a battery, this battery has some amount of current, and that same amount of current is what goes through that first resistor. And then the current splits. We've got some current that goes up, call that one I1. We've got some current that goes down, call that one I2, and this other one we'll call I3, with these being resistors 1, 2, and 3. The first rule, the first of the rules says that at a junction, like this one, all the current that goes into the junction, I3 is going into the junction, so what we want is that all the current going in is equal to all the current coming out. The only current going into this junction is I1, or is I3. The current coming out, we're going to have I1, and we're going to have I2. So that would be my junction rule equation at that location. Now, if I've got many junctions, I might have multiple junction rules that I write, but I'll never be able to write I'll never be able to properly use all of the junctions, the equations for each junction, because at some point there's a redundancy. In this case, where there are two junctions, here's the one, here's the other. If I wrote my junction rule equation for this second junction, I would get I1 plus I2 equals I3, which is the equation that I already have. If I have 12 junctions in a circuit, then the most junction rule equations I could possibly get away with using would be 11. It's always one fewer than the number of junctions. Now, if I have a junction like this and this, and then I have another junction here maybe, I'm not going to be able to use 3, because I've got, this is like one closed little piece, so those junctions make a pair that closes off. These junctions make a pair that closes off, so then I'd only be able to use 2. So the idea of kind of n-1 equations, that's a maximum. That's not a hard and fast rule. The other of Kirchhoff's rules says that I need to be able to have all my voltage taken care of, all my potential accounted for throughout one loop. We write for a battery this script E for a voltage. The reason, I guess I already started you off with some German, so the reason for this is that voltage, we used to call it once upon a time EMF, which stood for electromotive force. Motive of the electros, right? So it used to be electromotive force when this was first being developed, but then people realized, some people realized, this isn't actually a force, so this is actually kind of a bad name for this. Let's not call it electromotive force, but electromotive force in between was a long enough name to where people said, yeah, let's just call it EMF instead. Like, it's a little bit shorter to say. once this became recognized as no longer a force, we said, all right, let's get rid of that. But then the EMF part of it just kind of stayed around. From EMF, we get this curly E, this script E, and so that is used a lot of times for voltage from a battery, from some kind of a power supply. So then I said I was going to walk through what this looks like as far as tracing out the loop. From tracing out the loop, I want to pick a starting point, and I like to choose right before a battery. That's going to be my starting line. And now I'm going to just walk through, like walk around this loop. I'm going to go up here, and so the first thing that I encountered was this battery. I'm going to keep walking, nothing has happened yet. I've just hit bare wire the whole time. Now I hit a junction. So I have to pick a direction, and I'm going to go up this way. The next thing I encounter is resistor 1. So I'm going to say minus the voltage across resistor 1. So now I have made it past here. Keep walking. I've hit my junction. I need to keep moving, so I'm going to keep going. And I encounter this resistor. So I'm going to say minus the voltage across resistor 3. Keep moving, bare wire, and I have reached my starting line again, which means I have finished this thing. Once I finish this thing, I'm going to say equals 0. That would be a second equation. I have more, right? I have 3 unknowns, so I'm going to need a third equation, so I will come up with that. But that's the idea. I picked a closed loop, and I said all my voltage has to be accounted for. I didn't have to choose that loop. I could have gone down to this loop instead. So I could have also said, let's call this my purple loop. Now I'm going to look at a green loop. My green loop, I'm going to start from the same location, start moving, and I get E. I'm going to keep going, and now when I hit this junction, I'm going to say, nope, I'm going downward. Keep going, and I hit this resistor. So I'm going to say minus voltage 2. Keep moving, meet back up. Hey, another resistor. Minus voltage 3. And I already know how the rest of this story goes. I've got bare wire, a lot of bare wire, and I'm back at my starting point. So equals 0. These two equations are both true. And what that tells us, they're almost identical. So what that tells us is that the voltage across resistor 1 has to be equal to the voltage across resistor 2. These two that are in parallel will get the same voltage as each other. But let's look. Ohm's law says V equals IR. So where I've got V1, I'm going to replace this with I1 times R1. Where I've got V3 I did in blue. I'm going to replace this with I3 R3, and here it is again. I3 R3, and here's V2. That one I did in red. I2 R2. I have now 3 total equations with 3 unknowns. That is mathematically enough to be able to solve for everything. I don't have to do the step in between of saying minus V1 minus V3, I can just go minus I1R1 minus I3R3. That's okay. This thing was my V1. This thing was my V3. V2. V3. The reason that those are minuses, if you think of your voltage kind of as hills, then this loop rule idea is saying that I've got like a closed roller coaster circuit. I start out on my battery, so I start out at the top of a hill, and I start off with a hill. Then I hit my first resistor. That's going to take me down a little ways. Then I hit my next resistor. That's going to take me down a little ways. And when all is said and done, I get back, I better be right where I started. I need to be back at the start of this ride. This is not a picture of a boa constrictor eating an elephant. Some of you might get that, some might not. This is from The Little Prince. It's just a way for us to get back to where we started. So we need to be taking into account the entire voltage of our loop and end up right back where we started. I'll do separate videos going through a couple different methods of doing this. One that's just a longer version of this, or this for a more complicated situation. One that's a different shortcut, and we'll do some options.